excel in your career and take care of ourselves.
Yeah, good afternoon. Am I audible?
Yes.
Okay, thank you. Okay, we shall wait for 2 more minutes and start. Okay, so shall I start?
Yes.
Okay, thank you. So my screen is visible to you now?
Yes, it is visible.
Yeah, okay. So we shall start. So in the last class, what we have discussed is about machine design. Okay, so we all were there in that class and we were discussing about machine design and we have just gone through some basics of machine design. So today there is some continuation part, so that will be covered in this class. So the last class, what we have gone through is basic design consideration, design procedure, general consideration. So what do you mean by this types of general consideration and design, types of load, stress strain diagram, types of stressors, concept of creep, fatigue, SN curve, and endurance limit. These are the things what we have gone about in the last class. So what the first thing what we have discussed is how you do a design procedure. So this, hello. First thing what we have is design procedure. So design procedure, first criteria is what we are will be aiming is what is our need, then what are the mechanisms, we use, then we will be analyzing the forces, then we will be selecting the material, then design of elements, size and stresses, then modification, detailed drawing and production. These are the steps what we follow in machine design. Okay. So these are the things, general consideration, that means types of loads, stresses, etc. Motion of parts, selection of materials, form and size of parts, frictional resistance, convenient and economical features, use of standard parts, safety of operation, workshop facility, number of machines to be manufactured, cost of construction and assembling. Okay. These things we have discussed in the last class. That is why I am going a little bit fast. Okay. Then we have studied about what are the types of load, that is dead load, live load, suddenly applied impact load. Then we have studied about stress strain diagram. In that stress strain diagram, there first limit is, this is A is known as proportionality, B is the elastic limit, C is the yield point, 4 is the ultimate stress, 5 or E represents the breaking stress. Okay, this we have already discussed. Okay, so types of stresses we have discussed. Tensile stress is there, compressive stress is there, shear stress is there. Okay, these also we have discussed. Then also crushing stress is there. Then bending stress also we have discussed. Then torsional shear stress. These are the things what we have discussed about in the last class. Then we have discussed about equations relating to bending stress. What are the equations what we generally use for bending stress? The equation is M by I is equal to sigma by Y is equal to E by R. These are the things when you are designing a component in a machine design. These are the basic equations what we use. Okay, depending upon the feature what we are using or depending upon the material what we are using. Okay, then we have studied about principal stress and principal strain. Okay. Okay, so next what we are going to study is we have studied also creep. Creep, up to creep we have studied, I think. Okay, then so next is what we are going to study is fatigue. Okay. So last class we have discussed this one, but at the last minute only we have discussed. So we will go a little bit faster from here so that we can cover all the things. So what do you mean with fatigue? Fatigue is nothing but when a material is subjected to repeated stress. Repeated stress is acting on a material. It fails at the stress below the yield point stress. Okay. So when a load is, when a material is subjected to repeated stress for long interval of time, it fails stress due to yield point stress. It fails at the stress below the yield point stress. Such type of failure is known as fatigue. So the failure will be caused by a progressive crack formation, which is usually fine and microscopic size. The property is considered in designing shaft, connecting rod, springs, gears, etc. Okay, that is what we are going to. This property is considered in designing shaft. You have to understand connecting rod, springs, and gears, where continuous subjected to repeated stress. In these areas, repeated stress will be coming usually. Okay, so in these areas, we will be considering the fatigue load also. Next is endurance limit. So it may be defined as the safe maximum stress which can be applied to machine part working under actual condition. Okay. So if a machine is working, so what I mean by endurance limit is nothing but when a machine is working, okay, so there will be a machine will be having a rating to which up to which load it has to be applied. Okay, that safe load is known as entrance limit load or that load. Okay, entrance load. That means because if that above that load is acting for the material, acting on the material for a longer time, it may result in failure. So it is defined as the safe maximum stress which can be applied on the machine part working under actual condition. It is defined as the maximum value of completely reversed bending stress which a polished specimen can withstand without failure for infinite number of cycles. So that means the maximum safe stress. Okay. If it is above the stress, what happens? It will fail. Okay. So for example, if in a material, we are saying that it can withstand 100 Newton. Okay. Okay. So the maximum load it can withstand is 100 Newton. Sometimes if it is acting 110 Newton for a longer time, what happens? It will fail. Okay. So this is the criteria. So that is what is the maximum safe stress? 100 Newton. Okay. So what are the factors affecting entrance strength? Load factor, surface finish factor, size factor, reliability factor, and other miscellaneous factor. Okay. So next is what you are going to study is notch sensitivity. So notch sensitivity is nothing but it is defined as the degree to which actual stress concentration effect compares with stress theoretical concentration effect. So you have to study what is stress concentration, etc. That I will explain to you what I mean by stress concentration. So notch sensitivity is nothing but it is the ratio of actual stress concentration divided by theoretical stress concentration. Okay. So if you see, if you decide, the first thing in designing is, all of you, I think I am audible to you now. Okay. So first thing what you have to explain in factor of safety, what when you are using a machine design or when you are designing a material, okay, designing a machine component material, anything, the first thing what you have to consider is factor of safety. Okay. Okay. Factor of safety is maximum stress divided by design stress. It is very important. Okay. Okay. The factor of safety should be there. Within the factor of safety, if the factor of safety is not there, what happens? It will fail. Okay. It is defined as the ratio of maximum stress to the working stress. That is known as factor of safety. Okay. Ductile material, mild steel factor of safety. This is for if you are using a ductile material, the factor of safety is yield point stress divided by design stress. Because in ductile materials, there will be the stress strain curve will be, there will be a yield point over the stress strain curve. But when it comes to brittle material, it will fail. Okay, so that is the difference between ductile material. So factor of safety is yield point stress divided by working stress. But in case of brittle material, brittle means it will break. Okay, without reaching the yield point, it will break. So brittle material, which is the example of brittle material, cast iron. Cast iron is an example for brittle material. Ultimate stress divided by design stress will give you the factor of safety. So there are two criteria while designing. One is first thing is you have to find the factor of safety. So if it is for ductile metal, it is yield point stress divided by working stress. And if it is for brittle materials, it is ultimate stress divided by working stress. I think the concept is clear. Ductile material, because you may see, if you have any concern about these things, you may just see this graph. When it is a, okay, I will show you the graph. Okay, then you will understand why the definition is like this. So when you see this stress strain diagram now, this is for a ductile material. Ductile means mild steel. Okay, for example, is mild steel. It is for mild steel. So what happens is it will be having elastic proportionality limit, elastic limit, yield point. Okay, up to yield point only. After that yield point only, neck formation will take place and it will break. Okay, so that is why we are taking yield point stress divided by working stress. But in case of brittle material, if it is a brittle material, what happens is the graph will be like this only. Okay, so it will break over here. So that is what ultimate. So this will represent the ultimate stress in the brittle metal. For example, cast iron. Okay, for cast iron, it will be the ultimate stress. Okay, so then it will be ultimate stress divided by design stress. Okay, is it clear? Or working stress? Design stress and working stress are equal. Okay. So I think the concept, hello? Concept is clear, no? What is, pardon? Any question relating to this one?
No, sir, you can continue.
Okay. So this is what factor of safety. So I think the concept is clear. So when you are considering about a ductile material, you have to understand that there will be a value known as yield point stress. Then only it will be going to the breakage stage. So, but in case of brittle material, it is not like that. It is only having ultimate stress. It will break at the ultimate stress. So that is why when you consider factor of safety, it's ultimate stress divided by working stress for brittle materials. And when you consider it for ductile materials, it is yield point stress divided by design stress or working. Okay. So before selecting the factor of safety, an engineer should consider first thing the reliability of the properties of materials and change of these properties during service, the reliability of test results and accuracy applications of these results, the reliability of applied load, the certainty as the exact mode of failure, the extent of simplifying assumptions, the extent of localized stresses, the extent of initial stresses during manufacturing, the extent of loss of life in failure, and extent of loss of property. That means if you are, for example, when you are considering a material or a shaft, okay, to be designed, you have to keep all the things in the mind. First thing is that the shaft will be always subjected to some initial stress. Then if it is rotating, there will be so many stresses acting on this material. Example, bending stress will be there, torsional stress will be there. Okay. So these are all the criteria for the failure of that shaft. Okay. So while choosing a design for criteria for a shaft, what happens? You have to consider all these factors before designing or considering the factor of safety for a shaft material. That is what it is told in this explanation. So you have to consider all the factors affecting that material for the component what we are going to design. You have to consider all those things. Next is stress concentration. It is nothing but you can see over here. Don't confuse with anything. Stress concentration is like this. Okay. So there is a section like this, for example. Okay. So you all know that if water is flowing through this section, what happens? So water is coming in through this area, throughout the space. This much area is there, and water is coming through that area. Okay. What happens at this place? There is a change in area. So what happens here? What happens? The water concentration will increase. Is it clear? Any doubt? Okay, no. So the water will try to enter. All the water will try to enter this space, and here what happens? Concentration will be higher. Okay, that's the same concept here with stress concentration. So the stress is moving like this. At this place, what happens? When there is a change in area, there will be a discontinuity. Okay, that is what happening in stress zone. Okay, so you can see whenever a machine component changes the shape of its cross section, the simple stress distribution. So this stress distribution no longer holds good. The neighborhood of discontinuity is different. So discontinuity will happen. Okay. So this irregularity in stress distribution caused by abrupt changes of the form is known as stress concentration. It occurs for all kinds of stresses in the presence of fillet, notches, holes, keyways, splines, surface roughness, scratches, etc. Okay. So this happens in all these areas. You may see fillet, notches, holes, keyways, splines, surface roughness, and scratches. So the concept is simple. When a material is moving, when a stress is moving in this direction, okay, through this area, at this place, there is a change in area. What happens? Discontinuity will happen. Okay. Also, stress concentration will develop. Okay. So this is known as stress concentration. Okay. Next is what are the causes? So one is abrupt change in cross-sectional area. This is PS is cross-sectional area. Okay. Cross-sectional area. Then second thing is poor surface finish. Then localized loading. Then variation in material properties. These are the four things. What are the causes of stress concentration? Okay. So what are the methods to reduce stress concentration? So one is avoiding sharp corners, providing fillets, use of multiple holes instead of single holes, undercutting the shoulder part. Okay. So you see over here, when you can see here what happened? Corners are sharp. Okay. Corners are sharp. So here stress concentration is more. Okay. But you may see here there is a curve. Okay. Like without sharp, there is a curve over this. So here what happens? So the material will come like this, and there is a slight curve over this. So it will not create this much concentration, stress concentration as that of this sharp corner. So this is preferred or good. This is good. Okay. Then you can provide a slope like this also. Okay. This is also preferred. And one more thing is you can provide small holes before this. Okay. This is also a preferred criteria. Okay. Is it clear? Any doubt? Concept is clear? So without providing sharp corners, you can use a curve corner here. You can provide a small curve and a slope. Here you can provide small holes, or like this is this area, you can reduce this area. Okay. So that can analyze that there is a change in area. Okay. So that it can reduce the stress concentration line. Okay, now these are the things, methods of reducing stress concentration. Okay, so this is in the case of holes also, you do like this. Okay, you can see without providing sharp corners, you can provide corners with some bend. Okay, so curve, etc. So this is if we are drilling a hole at the center of a shaft. Okay, so this is not good. So when the stress is coming over here, it will be a discontinuity over here. But if you are providing two more holes like this, what happens? The stress in the earlier stage itself, there will be a discontinuity. So they will arrange according to this one. Okay. So here the stress concentration will be less compared to this part. Okay. Similarly, if you are using a tool or a nut, etc. Also, if you provide little bit length over here, it can understand there is a reduction in area, and it will be preferred or good as you consider. But in this case, it will be having higher stress concentration. But here you may see the cutting is above, so stress concentration will be less. Okay. But the thing is that we have to design according to our need. Okay. So what is the criteria you have to understand is that when you are designing a material, the thing is that the stress concentration should be less. So these are the methods in which we can reduce the stress concentration, or these are the ways in which the stress concentration can be reduced. I think it's clear, no? Concept. Okay. Next is theoretical or form stress concentration. The theoretical or form stress concentration factor, it is always with a K suffix T. Okay, that is maximum stress divided by nominal stress. Okay, nominal stress. So this KT depends upon the material and the geometry of the part. Okay, so it is the maximum stress in a member to the nominal stress at the same section based upon the net area. Okay, so theoretical stress form concentration factor is equal to maximum stress divided by nominal stress. So when you are designing a material in the machine design, you have to understand one thing: the stress concentration factor should be reduced to minimum. Next is steel. So actually, in mechanical or the machine design, most of the things or most of the materials or the compounds will be designed based on the material steel. Okay, so we have to study the types of steel and what are the designations of steel, how it is designated. That is what we are going to design. Okay, so the steels are carbon and low alloy steels, whereas the main criteria in the selection and the inspection of steel is the tensile strength or yield strength. So what is the specialty? Tensile strength or yield strength. According to Indian standard IS 1570, 1978, these steels are designated by the symbol FE. Okay, symbol FE. Okay, depending upon weather. Okay, so steel has been specified on the basis of minimum tensile strength or yield strength, followed by figure indicating the maximum tensile strength or yield stress in Newton per mm square. So unit is Newton per mm square. For example, if Fe290 means steel is having tensile strength of how much? 290 Newton per mm square. Okay, if it is Fe, 220 means the steel is having yield strength of 220 Newton per mm square. Okay, concept is clear now. If Fe290 means it is 290 tensile strength. If there is an capital E over there, that means it will be yield strength, 220 Newton per mm square. Why it is Newton per mm square? Just listen. What is stress? Load by area. What is the unit of load? Newton. Okay, area can be represented at mm square. That is why it is known as Newton per mm square. In some textbook, it will be Newton per meter square, but generally what we say is on the basis of Newton per mm square. Is it clear? The unit of force is Newton and area is meter square or mm square. Okay, that is why it is designated like that. Okay. So you may see Fe290, Indian standard designation Fe290 means tensile strength is 290, yield stress is 170, and minimum percentage elongation is 27. So when you are using a machine design or designing a machine component for your engineering or diploma purpose or whatever, when you study, there will be a data. Okay, a data book will be there. Okay, so the values can be, you can take the standard values from the data book and you can substitute in the problem. Okay, so that is why this table is given over here. Okay, so it is Fe290 is plain drawn or enameled. Parts of tubes or oil well casing, steam water, air passage, cycle, motorcycle, automobile tubes, rivet bars, and wires. This is what they are used. Okay. That means they are used for plain drawn or enameled parts. Okay, plain drawn or enameled parts. So oil well casing, steam water, air passage, cycle, motorcycle, automobile tubes, river bars, and wires. Okay, that is the use of this Fe290 and Fe220. E is nothing but yield strength will be what? Yield strength will be 220. So there are other steel like this. Next is Fe310. 310 means the tensile strength will be 310 Newton per mm square. 230 means yield strength will be 230 Newton per mm square. Fe330 means 330 Newton per mm square will be its tensile strength. Fe250 means 250 Newton per mm square, which will be its yield stress. Similarly, Fe360 means 360 Newton per mm square, it will be its tensile strength. Similarly, Fe270 means 270 Newton per mm square will be its yield stress. Okay, so this Fe310, these steels, that means this Fe310, FEE230, Fe330, FEE250, they are used for locomotive carriage, car structures, crew stock, and other general engineering purpose. Okay, this Fe360 is used for chemical pressure vessels and other general engineering purpose. Okay, I think this is how it is designated. You have to understand one thing. Fe290 means 290 Newton per mm square will be its tensile strength, and FEE220 means 220 Newton per mm square will be its yield strength. Okay, I think the concept is clear for you now. Okay. Next is steels are designated on the basis of chemical combustion, C40 like that. Okay, so according to Indian Standard 1570, Part 2, Section 1, 1979, Reform 1991, the carbon steel are designated in the following order. Figure indicating 100 times the average percentage of carbon content. Then letter C, figure indicating 10 times the average percentage of manganese content. Okay, you may see 20C8. These type of C's are there. Okay, so the figure after multiplying shall be rounded off to near integer. So for example, 20C8. So you may see 20C8 is a carbon steel. Okay, 20C8 is the value of carbon. Okay, so here the percentage of carbon will be 0.15 to 0.25. Actually, that is what the value of this carbon percentage represents 0.15 to 0.25. So what they will do is they will take the 0.15 plus 0.25 by 2. So what will be, you will get 0.2. They will take the average. So this 0.2 into 100, when you do, what happens? You will get how much? Sorry, 100, but you will get 20. Okay. So this will be the first thing, 20. Then you will write the symbol C. So it is having manganese percentage up to 0.6 to 0.9. 0.6 plus 0.9 by 2. So what is this 0.6 plus 0.9? That is 1.5 by 2. It is 0.75. We will not take 0.75. We will be rounding to the next value. So it will be 0.8. You have to multiply this into 10. What you will get? 8. So this is how it is designated. Okay. Any doubt? Concept is clear now? If it is not clear, I will explain it once again. Please listen. So is if you are having a steel 20C8. Okay, so 20 represents the carbon percentage. Okay, then 8 represents the manganese percentage. Manganese percentage. Okay, no. Okay, 20 represents the carbon percentage and 8 represents the manganese percentage. So how? So if it is 20C8 means the carbon content will be 0.15 to 0.25. Okay, percent. So what you do is you will take the average of 0.15 plus 0.25 by 2. What is that? 0.40 by 2, it will be 0.2. Okay. Then you have to multiply this 0.2 into 100. You will get 20. That will be your first letter, 20. Then you have to add C to that. Then you have to find the manganese percentage. Manganese percentage is 0.60 to 0.90. So 0.6 plus 0.9 divided by 2 or 1.5 by 2, it is 0.75. Okay. So you should not take 0.75. You have to round to up. Next value, it will be 0.8. Then you have to multiply this 0.8 into 10. You will get 8. That is the value we will be putting over here. So 20C8 you will get. I think the concept is clear now. Any doubt? Okay. Shall I proceed further?
Yes, sir. Clear,
So,
sir. Clear.
okay. So there are some of the standard values, that is 4C2. 4C2 means carbon content is 0.08 and manganese content is 0.4. Okay. It is dead soft steel generally used for electrical industry. Okay. Then 5C4. 5C4 means 0.10 will be the carbon content, 0.5 will be the manganese content. These steels are used when cold formability is the primary requirement. In this rimming quality, they are used as sheet strip, rod, wire, especially where excellent surface finish and good drawing qualities are required, such as automobile body, fender stock, hoods, lamps, oil pans, and multiple deep drawn and formed products. They are also used for cord heading wires, rivets, low carbon wire products. Okay, these are used for wire products only. That is 7C4. 7C4 means 0.12 will be the carbon percentage, 0.5 will be the manganese percentage. 10C4 means 0.15 will be the carbon percentage, and 0.3 to 0.6 will be its manganese percentage. Okay, so these are the things what you are going to understand. So most probably you will be 20 C8, 30 C8, like that steel is mostly used over here. 10 C4 means 0.15 will be its carbon content, and 0.3 to 0.6 will be its manganese content. Case hardened means they are camshaft, cams, light duty gears, worms, Georgian pins, spindle, poles, ratchets, chain wheels, tappets, etc. Okay, what do you mean by case hardened? Case hardened means the steel outer portion will be hardened. Okay, that is known as case hardened. Okay, then 14C6 is the carbon percentage will be 0.1 to 0.18 and manganese percentage is 0.4 to 0.7. Then 15C4 is 0.20 will be the carbon percentage, and 0.3 to 0.6 will be its manganese percentage. It is used for lightly stressed parts. These materials, although easily machinable, is not designed specially for rapid cutting, but are suitable for cold web such as bending and riveting. Where bending and riveting is necessary, they are used. Okay, where bending and riveting. Okay, in case of bending and riveting, they are used. Okay. Where these processes have to be done, we are using this type of 15C4 steel. Next is free cutting steel. According to Indian standard, carbon and carbon manganese free cutting steels are designated in following. Figure indicating 100 times the carbon percentage, letter C. Figure indicating 10 times the average percentage of manganese, and symbol as followed by the figure indicates 100 times the average content of sulfur. Okay, instead of sulfur, if lead is added to make steel free cutting, the symbol PB may be used. Okay, so that is what free cutting steel means. Free cutting means steel means you may see same procedure. You see 10 C8 S10. Okay, S10 means what will be the carbon content? 0.15 will be its maximum carbon content. Then any doubt? Then C will be carbon. 8 will be what? Its manganese percentage, that is 0.6 to 0.9. S represents what? Sulfur content. Okay. So this is the sulfur value, that is 0.8 to 0.1. Okay. This is what free cutting steel. You have to understand. First will be its carbon content, that is whatever into 100. Then letter C. Then the figure represents the manganese content. Okay. Then sulfur into sulfur, and the next to sulfur, it will be the sulfur content. Okay, this is how free cutting steels are designated. You may see over here 10 C8 S10. So 0.5 will be its carbon content, 0.5 to 0.3 will be its silicon content, 0.6 to 0.9 its manganese content, 0.8 to 0.13 its sulfur content, and phosphorus is 0.6. Only thing what you have to consider is carbon, manganese, and sulfur. Okay, if lead is added in place of sulfur, what will come? PB will come. Okay. So these are the designations. 14 C14 S14, 25 C12 S14, 40 C10 S18, 11 C10 S25, 40 C15 S12. These are the designations of free cutting steels. Okay. 14 C14 S14 means carbon content is 0.1 to 0.8, manganese content is 1.2 to 1.5, sulfur content is 0.1 to 0.18. 25 C12 F14 means 0.2 to 0.3 will be its carbon content. Its manganese content is 1 to 1.5, sulfur content is 0.10 to 0.18. 40 C10 F18 means carbon content is 0.35 to 0.45. Then manganese content is 0.8 to 1.20 and sulfur content is 0.14 to 0.22. Similarly, 11 C10 S25 means 0.8 to 0.15 is the carbon content, 0.8 to 1.20 is the manganese content, and 0.2 to 0.3 is the sulfur content. Similarly, 40 C15 S12 means 0.35 to 0.45 is the carbon content, 1.3 to 1.7 is the manganese content. Similarly, 0.08 to 0.15 is the sulfur content. Okay, so these are where they are used. Okay, that you can read. So this is how pre-cutting steels are designated. Next is Indian Standard Low and Medium Alloy Steels. According to Indian Standard 1762 Part 1, 1974 reaffirmed 1993 low and medium alloy steels shall be designated in follow. That means figure represents 100 times average carbon content, chemical symbol for alloying element each followed by the figure at the average percentage content. So chromium, cobalt, nickel, manganese, silicon, vanadium. Okay, these are the factors what will be using. These are the contents what will be using. If they are used into 4 times, if Al, Be, V, Pb, copper, Nb, Ti, Ta, Zr, molybdenum, Mo are used, zirconium, titanium, okay, copper, lead, aluminum, like that. What are the material used? Then you have to multiply it to 10. Okay, that is what we will use. Phosphorus, sulfur, and nitrogen is used. You have to multiply it by 100. Okay, this is how the ratio is coming. Okay, so you can see 11 Mn2. That means carbon content is 0.16, silicon content is 0.1 to 0.35, and manganese Mn is 1.3 to 1.7. Okay, so if it is manganese Mn, you have to multiply it by 4. So here what is that? 1.3, okay, plus 1.7. So it will be 3, no? So that is 11. It will be 3. So 3 by 2, it is 1.5. You can having an average value of 1.5. So whatever 1.5 is there, you have to multiply that 1.5 into 4. You will get this content 11 manganese 2. Okay. Then 20 Mn2, 27 Mn2, then 37 Mn2, 20 Mn2 means carbon content will be 0.16 to 0.2. For manganese content will be 1.3 to 1.7. Okay. Similarly, 27 Mn2 means carbon content is 0.22 to 0.32. Similarly, manganese is 1.3 to 1.7. Okay. This is how you will be naming this alloy steels. So in alloy steel, whatever alloying component is there, if it is manganese, you will be representing by its name. If chromium is there, Cr will be represented over here. That you can see 40 Cr1 means chromium content is represented. 50 Cr1 means chromium is there. Okay. Here when you see here, manganese Mn is also there. Molybdenum Mo is also there. Okay. These are the two contents what we are applied over here. Here manganese is there, molybdenum is there. Here chromium is there, molybdenum is there. Okay. On the basis of the impurity or the alloying element, you will be having this equation. Okay. I think the concept is clear. Okay. This is just a concept how the material is selected. Okay. You should not study this table or etc. The thing is that you have to just remember what is there over here. Okay. How this is represented or designated. That is the important thing over here. Okay. Next is Indian Standard High Alloy Steel. According to Indian Standard 1760 to 1974, reaffirmed 1993, high alloy steel, that is stainless steel and heat resisting steel. These are known as high alloy steels. That is stainless steel and heat resisting steel are designated by the letter X. Figure indicating 100 times the percentage of carbon. Chemical symbol of alloying element each followed by a figure of its average percentage rounded off to next integer. Okay. Chemical symbol to indicate specially added element to allow desired properties. Okay. So one more thing, you may having a doubt over here why you are so 11 Mn2. There is a doubt over here why here it is 2. You will be having a doubt. No, it is 1.3 plus 1.7 by 2. It will be what? 1.5 will be your average value. The thing is that you will be rounding this average value to 2. Okay. Thing is that it should be only having a maximum of 4. Okay. Above 4, it will not be added. That is what 4 represents over here. It's clear, no? If it is, it will, that means this multiplying factor 4 means it cannot be above 4. Okay. Your value is 4. So the maximum value is 10. Here the maximum is 100. Okay. So X10 X means it is the letter X. 10 means the carbon content. Chromium 18, nickel 9. Okay, so means alloy steel with average carbon content of 0.1 percentage, chromium 18 percentage, nickel 9 percentage. Concept is clear, no? X10, Cr 18, Ni 9 means X into X is the symbol which is what 10 means 0.10 percentage of carbon, 18 percentage chromium and 9 percentage nickel. Okay, I think the concept is clear. X10 means 0.10 percentage of carbon because carbon content into 100 you have to do. So 0.10 into Cr 18 means 18 percentage of chromium is there, 9 means 9 percentage of nickel is there. Okay. Then Indian standard designation of high speed tool steel. So according to Indian standard 1762 part 1 1974 reaffirmed in 1993 high speed tool designated by X suffix T. X suffix T means it is a high speed steel. If X is only there, that is heat resisting steel or high alloy steel. Okay. So that is XT means high speed tool steel. If it is X, it is high alloy steel. Okay, I have to understand that. XT means high speed tool steel. Okay. Figure indicate 100 times of percentage of carbon content, chemical symbol of alloying element, each followed by the figure of its average percentage content rounded off to nearest integer, chemical symbol to indicate specially added element to attain the desired property. Okay, so here you may see XT75, W18, CR4, V1. That means it is a tool steel. You have to understand this is a tool steel. The tool steel, you have to understand that with 0.75 percentage of carbon is there, carbon, then W will be what? Tungsten. It will be 18 percentage. W means tungsten. It will be 18 percentage. Similarly, chromium, Cr means chromium, it will be 4 percentage, and V is vanadium, it is 1 percentage. I think the concept is clear. XT75, W18, CR4, V1 means XT, it means tool steel, 0.75 percentage of carbon is there, tungsten 18, W represents the tungsten. Tungsten 18 percentage is there, chromium 4 percentage is there, similarly vanadium 1 percentage is there. Okay, so remember that if it is X, it is high. What is that? X is what? High alloy steel. If it is X, it is high alloy steel. You have to represent X, it is high alloy steel, and XT means tool steel. Okay, high speed tool steel. You have to understand that. Okay, if it is X, high alloy steel, if it is XT, high speed tool steel. Okay, this is how they both are designated. Okay. Okay, I think the concept is clear. So you have to understand that if it is X10, Cr18, N9 means it is a high alloy steel with 0.1 percentage of carbon, chromium 18 percentage, and nickel 9 percentage, and it is an high alloy steel. It is very important. You have to understand that it is an high alloy steel. Now, when it comes to XT, you have to understand that is high speed tool steel. So XT, XT75, W18, CR4, V1 means XT, it is high speed tool steel, 0.75 percentage of carbon, then tungsten 18 percentage, chromium 4 percentage, and vanadium 1 percentage. This is how it will be going. Okay, I think the concept is clear.
Sir, tungsten is also a metal.
Yeah, it's like that, it's a metal, but what they are doing is they are adding these elements to the steel to improve the properties of steel. Tungsten is also there. It is also there in our periodic table.
Okay, sir.
They are added to the steel to improve its properties. So, because it has to be prepared to a tool steel, that is why tungsten is there. Next, you have to study what are the different theories of failure which will lead to failure of a material. One is maximum principal stress theory. It is also known as Rankine theory. Similarly, maximum shear stress theory, it is known as Guest or Tresas theory. Maximum principal strain theory, which is known as Stein-Mendel theory. Maximum strain energy theory, also known as Hayes theory. Maximum distortion energy theory, also known as Henke von Mises theory. These are the theories of failure. These are the theories in which what happens? Failure will happen. These are the theories which suggest that how the failure is happening. Okay, so these are the 5 theories. One is maximum principal stress theory known as Rankine theory, maximum shear stress theory known as Kester-Tresas theory, maximum principal strain theory known as Stein-Mendel theory, maximum strain energy theory, which is also known as Hayes theory, and maximum distortion energy theory, also known as Henke von Mises theory. According to maximum principal stress or normal stress theory. Okay, that is what we are going to study. That is known as Rankine's theory. So, according to this theory, the failure or yielding occurs at a point in a member when the maximum principal stress or normal stress in a biaxial stress system reaches the limiting strength of the material in a simple tension stress. So, this simple. If you are having a conducting a simple tension test, for example. Okay. So you know that there is a limiting strength for the material. Okay. So here failure occurs when the maximum principal or normal stress in a biaxial stress system reaches the limiting strength of the material. If they are equal, what happens? Failure will happen. Okay. Since the limiting strength for a ductile material is yield point stress, I have told you limiting strength is yield point stress, and for brittle material, it will be what? Ultimate stress. So, above theory, factor of safety is consideration. The maximum principal of normal stress theory in a biaxial system is given by sigma T1 is equal to sigma YT divided by factor of safety. Sigma YT means yield point stress. Yield point stress will be coming in which material? Ductile material. Okay, yield point will be coming in ductile material, and if it is for brittle material, it is sigma U divided by factor of safety. So what is that sigma U for ultimate stress? It is for what? Brittle materials. Okay. Okay. So you'll be having a doubt with maximum principal stress or normal stress that we have studied in the last class. If you are not remembering it, I will explain it. What is principal stress? Just see. This one. Principal stress. Planes which have no shear stress are known as principal planes, and the direct stress along these planes are known as principal stress. Okay, the stresses acting where there is no shear stress, the stresses acting in that planes are known as principal stress. Okay, the planes on which maximum shear stress act is known as planes of maximum shear. Okay, so this is when a member is subjected to biaxial stresses. Okay, then the normal and shear stress are obtained is discussed below. Sigma T1 is equal to sigma 1 plus sigma 2 by 2 plus or minus 1 by 2 root sigma 1 minus sigma 2 the whole square plus 4 whole square. So to understand principal stress means when the stress are acting in the along the plane where there is no shear stress. Okay, that was your concept what we have studied in the last. Okay, then when you are going to deeper through this portion, next thing is we have already told you the last before in the beginning of the class itself. I have told you I have drawn that stress strain diagram over here. That stress strain diagram itself we have told you if it is a ductile material. Just wait, let me reach that point. Okay, so you may see over here. We'll rub it and explain. is nothing but for a ductile material, you have to understand that for ductile material, this will be the yield point. Okay, then only neck formation and breakage will happen. But you have to see for ductile material, there will not be any yield point. Here, what will come? Ultimate stress will come. Okay, here, here, it will be your ultimate stress. Okay, here this will be breakage. Okay, this is a specialty of ductile material. If it is brittle, only one stress is the ultimate stress. Ultimate stress itself for glass, if its value is reaching the ultimate stress, glass will break. It is a brittle material. Okay, you have to understand. Okay. But when you consider mild steel, it is a ductile material. Okay, so that is what sigma T1 is ultimate stress sigma T1 is sigma YT by factor of safety. YT represents ultimate stress. It will be for ductile material. Sigma U by factor of safety. It will be for brittle material. Okay. So next is maximum shear stress theory. Okay. So what happens? The failure will be happening when the shear stress in a biaxial system reaches the value equal to shear stress at the yield point in a simple tension test. So tau max will be equal to tau YT divided by factor of safety for which one? Brittle materials, and tau U, that is ultimate shear stress for ductile materials. Okay. Okay, that is a specialty. So, according to maximum shear stress theory, according to this theory, the failure of this is single sentence only. When I have changed it to PDF, I think just dislocated. Okay. According to this theory, the failure or yielding occurs at a point in a member when the maximum shear stress in a biaxial stress system reaches a value equal to shear stress at the yield point in a simple tension test. So tau max is equal to tau YT divided by factor of safety. What is tau YT? It is ultimate. Sorry, tau YT is yield point shear stress. Okay. So shear stress at the yield point. Okay. Tau YT. If it is tau U, it is ultimate shear. Okay. Ultimate shear. Next is maximum distortion energy theory. According to this theory, the failure or yielding at a point in a member occurs when the distortion strain energy or shear strain energy per unit volume in a biaxial stress system reaches the limiting distortion energy. Okay, that is distortion energy at yield point per unit volume as determined by simple tension test. So it is sigma T1 square plus sigma T2 square minus 2 sigma T1 plus sigma T2 is equal to sigma YT divided by factor of safety the whole square. Okay, sigma YT is yield point stress divided by factor of safety the whole square. Okay, so according to this theory, the failure or yielding occurs at a point in a member when the distortion energy, the shear strain energy per unit volume in a biaxial stress system reaches the limiting distortion energy. That is limiting distortion energy means distortion energy at yield point. That is limiting distortion energy per unit volume as determined by a simple tension test. This is what maximum distortion energy theory is explained. So these are the main topics comes under machine. So you have to understand that these theories are important while designing a material. Okay. So maximum principal stress theory and maximum shear stress theory means principal stress means you have to understand that according to this theory, the failure of a member happens when the maximum principal stress or normal stress in a biaxial stress system reaches the limiting strength of the material in a simple tension state. Similarly, according to maximum shear stress theory, the failure or yielding occurs at a point in a member when the maximum shear stress in a biaxial stress system reaches the value equal to shear stress at the yield point in a simple tension test. So tau max is equal to tau YT divided by factor of 6. Similarly, maximum distortion energy theory, according to this theory, the failure or yielding occurs at a point in a member when the distortion strain energy per unit volume in a biaxial stress system reaches the limiting distortion energy or distortion energy at yield point per unit volume as determined by a simple tension. So the value is sigma T1 the whole square plus sigma T2 the whole square minus 2 sigma T1 plus sigma T2 is equal to sigma YT by factor of safety the whole square. Okay, these are the various theories of failure. I think the concept is clear. What is stress, what is strain, how fields are designated, what are the steps in machine design. These all are the things what you have discussed with the two classes. I think that you have gone through the concept of this machine design. Okay. So you have to understand that while designing a material, factor of safety has a very important role. Similarly, we have already studied about stress concentration, then principal stress, principal planes, then what are the steps in design process, etc. Okay, so we have discussed an overview of all the machine design topics. Okay, if you have any doubt, you can have a discussion. Otherwise, we can wind up the class. Okay, it's according to you. Okay, I think there is no doubt in the session. Okay, so shall we wind up? Yeah. Okay. Thank you all.
Okay, sir.
Okay. Thank you.
Okay, sir.
Okay. Good night. Okay.
Good night, sir. Thank you.
Good night, sir. Good night.